When Suzuki released the GSX 1300R Hayabusa in 1999, it was not building a motorcycle to compete. It was building a machine to end the competition entirely. Designed in the wind tunnel, tested on open roads, and refined with only top speed in mind, the Hayabusa became the fastest production bike the world had ever seen. But beneath the press headlines and spec sheets were a series of choices few riders ever recognized. From quiet revisions, forgotten components, and subtle engineering risks that shaped the machine from the inside out, here are the 10 unknown, shocking secrets about the 1999 Suzuki Hayabusa you have never heard of. Number 10. Exhaust-driven ram air that boosts power at top speed. Most riders know the 1999 Hayabusa for its speed, but few realize how that speed was actually achieved. The top-end numbers were not the result of displacement alone, or even raw horsepower on paper. They came from a system that quietly changed how the engine breathed, and more importantly, when it breathed best. Hidden behind the aerodynamic bodywork of the first-generation Hayabusa was one of the most misunderstood performance features of its time, Suzuki's pressurized ram air system, and it worked in ways that most riders never saw, unless they were riding flat out. Suzuki designed the Hayabusa's body in the wind tunnel for a reason. Every curve, every intake duct, every line across the fairing had a specific aerodynamic job, but it was not all about reducing drag. Part of that design was focused on harnessing incoming air and feeding it into the engine under pressure. Large scoops on both sides of the nose, just below the headlight, were shaped not for looks but for function. As speed increased, these ducts captured oncoming air and funneled it into a pair of sealed intake tubes that connected directly to the airbox. The system itself was simple in concept. The faster the bike traveled, the more air was forced into the intake at higher pressure. This increased the air density entering the combustion chambers, allowing for more fuel to be burned and more power to be produced. At rest or at low speeds, there was little effect, but at speeds above 130 miles per hour, the gains began to show. And by the time the Hayabusa reached its top speed of approximately 194 miles per hour, the airbox was seeing pressure increases equivalent to an estimated 1 to 2 pounds per square inch over ambient. That may not sound like much, but it translated to real horsepower. Dyno tests of the GSX 1300R showed a peak output of 173 horsepower at the crankshaft under static conditions. However, when factoring in the ram air effect at high speeds, real-world power was estimated to reach as high as 178 to 181 horsepower. This was not due to tuning nor software trickery. It was pure airflow, driven by the shape of the bike and the velocity of the road. One of the more unusual aspects of Suzuki's design was how the exhaust system contributed to the intake effect. By carefully managing back pressure and tuning the header lengths to match engine pulses, Suzuki created a low-pressure zone behind the exhaust valves. This helped pull spent gases out more efficiently, which in turn allowed the intake charge to fill more completely. Combined with the pressurized intake air, this gave the engine a kind of natural supercharging effect, minimal in numbers, but powerful in the context of high-speed endurance. It is worth noting that this system had no moving parts. There were no electronic valves, no fans, and no active sensors adjusting the flow. The effect was entirely passive, driven by physics and speed. That also meant it could not be simulated on a standard dynamometer. Many early Hayabusa owners were confused when dyno results fell short of magazine claims. The missing piece was motion. Without the ram air effect, the bike could not reach its full potential, at least not in a controlled environment. This design also shaped how the Hayabusa felt at high speeds. Riders reported a surge of additional thrust above 150 miles per hour, a zone where most engines start to flatten out. The Suzuki kept pulling, not because of gearing or torque curves, but because the air itself was helping it breathe. That effect became part of the legend, part of the reason the 1999 Hayabusa felt different from everything that came before it. So the next time someone quotes a static horsepower figure for the GSX 1300R, remember that the real story only begins when the road is long, the throttle is wide, and the wind is working with you, not against you. Because when Suzuki built this bike, they designed it for speed you could feel. And sometimes, the secret to going faster was hidden in the very air rushing past your mirrors. Number 9. Aluminum frame inspired by samurai armor for rider protection. Before the Hayabusa ever reached its top speed, before the engine turned over, and before the fairing met the wind, Suzuki had already made one of its boldest design decisions. It was not in the powertrain or the suspension, it was in the frame. This was not a reworked chassis borrowed from a race bike. It was a purpose-built structure that drew directly from an unexpected source: samurai armor. During early development, Suzuki's design team explored traditional Japanese protective gear not for symbolism, but for engineering logic. Samurai armor was constructed to redirect impact, absorb force, and shield the body without restricting movement. That principle guided the layout of the Hayabusa's twin-spar aluminum frame, which was crafted to handle massive longitudinal and torsional loads while maintaining composure at high velocity. The frame was a blend of cast and extruded aluminum sections, shaped to manage stress like layered plating. The top spars arched over the engine with deliberate curves, echoing the shape of a kabuto helmet, while the side beams formed a structural barrier that followed the same logic as the lamellar chest armor of the Dumaru. In both cases, strength came not just from mass, but from form. The contours were meant to channel energy away from the center, deflecting rather than absorbing whenever possible. That geometry was more than stylistic. Under load, the chassis kept the bike planted and predictable. The longer wheelbase and heavier mass certainly contributed, but it was the stiffness of the main frame that gave the Hayabusa its stability. At speeds where most bikes began to show nervous flex or unsettled steering, the Suzuki remained calm. The rider felt less of the road, not because the suspension softened it, but because the chassis filtered it out. Part of that behavior came from the way the aluminum was distributed. Heavily reinforced castings were placed at high-stress zones around the steering head and swing arm pivot, while hollow extrusions filled the spans in between. This selective stiffness allowed the Hayabusa to resist twist during hard acceleration and braking, without transmitting every vibration to the rider. The effect was subtle, but it changed the way the bike responded during sustained high-speed travel. There was also a practical side to the design. In the event of a slide or collision, the frame helped protect both the rider and the critical engine components by acting as a primary deflection point. Like a breastplate, it bore the brunt of external force, spreading it across the spars rather than allowing it to concentrate at a single failure point. It was not marketed as a safety feature, but it behaved like one. It is easy to overlook the importance of a frame when the numbers are all about speed, but the truth is, the Hayabusa's ability to remain composed at extreme velocity had less to do with power and more to do with how the bike held itself together. The more you learn about this machine, the less it feels like anything else from its time. If you're seeing the Hayabusa in a new way, hit like, subscribe, and keep watching. We're not done uncovering what made it different. Number 8. Extremely rigid twin-beam frame hides a rock-solid secret. The Hayabusa was built for speed, but the real brilliance was how that speed was controlled. A machine that could approach 200 miles per hour could not afford to feel vague, unsettled, or imprecise. That level of performance required a frame that did more than hold everything in place. It needed to eliminate doubt, and that is exactly what the Hayabusa's twin-beam aluminum frame was engineered to do. But what most riders never knew was that buried inside this frame was a level of rigidity that exceeded even Suzuki's own superbikes of the time. On paper, the twin-spar layout looked familiar. It used two large beams running from the steering head to the swing arm pivot, cradling the engine in between. This was a common layout by the late 1990s, seen on everything from the GSX R Series to Yamaha's R1. But the Hayabusa's version was heavier, broader, and significantly more reinforced. Not because it needed to meet racing homologation rules, but because it had to remain completely composed at continuous high speed, under load, and across long distances. That was a different kind of demand entirely. Suzuki engineers increased the frame's torsional rigidity by reinforcing internal ribbing within the spars, adding localized bracing near high-stress zones, and enlarging key contact points at the neck and pivot. The result was a chassis that was stiffer than the contemporary GSX R 750 by an estimated 15%, even though the Hayabusa was not marketed as a track machine. That stiffness gave the chassis a neutral behavior under acceleration and braking, but it also added something harder to quantify: predictability. The more rigid a frame is, the more consistently it responds to input. At lower speeds, the effect is subtle, but when wind resistance builds and cornering loads increase, even small amounts of chassis flex can cause instability. On many high-performance motorcycles, that flex is accepted as part of the design. The Hayabusa approached it differently. By overbuilding the frame, Suzuki ensured that the rider never had to second-guess what the bike was going to do next. Whether leaned over in a sweep or climbing through high-gear acceleration, the response remained exact. This design came with trade-offs. The added stiffness transmitted more vibration to the rider, especially at mid-range engine speeds. And because the frame was not engineered to flex with the suspension, the tuning window for ride comfort became narrower. But Suzuki made a deliberate choice. At the speeds the Hayabusa was capable of sustaining, rigidity became a form of insurance. It kept the geometry stable, the wheel alignment constant, and the bike composed through wind buffeting, hard downshifts, and heavy throttle transitions. It also allowed Suzuki to mount the engine as a semi-stressed member, with the frame carrying structural load across the top spars, while the engine absorbed lateral force. This setup helped centralize mass and simplified the load path through the chassis, reducing torsional twist and improving long-range structural integrity. In practice, that meant the Hayabusa could carry high speed for hours without developing fatigue cracks or alignment issues, something most track-focused frames were never designed to manage. Most riders who owned the early GSX 1300R never pulled the frame apart or measured flex under load, but they felt it in every fast corner that held its line, in every highway pass that stayed planted, and in every long ride that ended without a rattle or creak. The real secret of the Hayabusa was not how fast it could go, it was how solid it stayed while going there. Because when a machine is built to outrun everything else on the road, it needs a backbone that never flinches, and this one had it. Number 7. Gear-driven counterbalance that lets the engine be a stressed member. There are few components on a motorcycle engine that go unnoticed more often than the counterbalancer. It does not add power, it does not improve top speed, and it is never featured in a spec sheet headline. But on the 1999 Hayabusa, that counterbalancer did something most riders never expected. It unlocked the potential to turn the engine into a structural part of the chassis, and that quiet piece of engineering played a crucial role in how the Hayabusa held itself together under pressure. The Hayabusa engine was large, heavy, and powerful, but it was also smooth. That smoothness was not the natural result of balanced internals. It came from a specific mechanical solution, a gear-driven secondary counterbalance shaft mounted low in the crankcase. Its purpose was to offset the vibrations caused by the large displacement inline-4 layout, particularly the vertical shaking forces that increase with engine speed. Rather than relying on rubber mounts or passive dampers, Suzuki engineered a precise gear train system to rotate the balancer shaft in the opposite direction of the crankshaft's secondary forces. This solution made the engine feel calm and composed, even as revs climbed into the 5-digit range. More importantly, it reduced the structural stress passed into the frame. Without that counterbalance, the engine would have required isolating mounts to keep vibration from fatiguing the chassis or exhausting the rider. But with it in place, Suzuki had another option: fix the engine directly to the frame and let it become a load-bearing element. That decision changed everything about how the bike was built. Instead of floating the engine within soft bushings, Suzuki bolted it directly between the twin spars, using it to carry lateral and vertical loads. This turned the engine into what engineers call a semi-stressed member, helping to stiffen the midsection of the chassis while saving weight and improving packaging. The counterbalancer made that possible by eliminating the harmonic forces that would otherwise damage the mounting points over time. The advantage was more than structural. A rigid engine mount allowed for tighter geometry and better mass centralization. The entire drivetrain became part of the backbone, rather than a component suspended within it. That gave the Hayabusa a feeling of solidity and unity under throttle, especially during aggressive acceleration or rapid side-to-side transitions. The frame and engine worked as a single mechanical system, rather than two parts held loosely together. There were long-term benefits as well. The added rigidity from the engine mounts helped prevent microflex in the chassis, which is a common fatigue point in high-mileage performance bikes. And because the counterbalancer was gear-driven rather than chain-driven, it maintained precise timing across the entire rev range without the need for frequent adjustment or replacement. It was not only smoother, it was reliable. The counterbalancer never drew attention to itself. It made no noise, required no input, and had no dramatic visual presence. But it was one of the quiet forces that held the Hayabusa together, both mechanically and conceptually. Because when Suzuki designed the GSX 1300R, they knew that every part had to carry its share of the load. And in this case, the part that carried the weight was also the one that made the whole bike feel like it was never working hard. Number 6. Instrument cluster. Top 220 miles per hour before the gentleman's agreement. There is a difference between designing a motorcycle to go fast and building one that is meant to remind you of it every time you look down. On the 1999 Suzuki Hayabusa, that reminder came in the form of a number, not a performance figure printed in a brochure, but a needle that swept toward a threshold few machines had ever reached. Buried within the analog cluster was a signal of intent, a speedometer that topped out at 220 miles per hour. It was more than a display. It was a quiet challenge, printed on the dash just before the industry agreed to stop trying. The instrument panel on the first-generation Hayabusa followed a traditional layout. 4 analog dials, evenly spaced and symmetrically designed, carried information in a direct, no-nonsense fashion. The tachometer sat front and center, flanked by the speedometer on the right and auxiliary gauges on the left. The numbers were clear, the faces uncluttered, and the bezels finished with a subtle brushed metal edge. But the detail that set it apart from every other production motorcycle on the market was its final digit, 220 miles per hour. At the time, no factory motorcycle claimed to reach that speed. The Hayabusa's true top end sat closer to 190 to 195 miles per hour, depending on conditions. But Suzuki left room on the dial, not to exaggerate, but to prepare. The company knew exactly what it had built, and they knew the bike had more in it than anyone had ever tested in public. That upper reach on the speedometer was not fantasy, it was headroom. This detail mattered more than most riders realized, because it was one of the last times a manufacturer could print that kind of number without consequence. In the months following the Hayabusa's release, pressure mounted from regulatory bodies and governments concerned about rapidly escalating motorcycle performance. Conversations among major manufacturers began to take place, quietly and informally at first. The result was a voluntary decision. Starting in the year 2000, production motorcycles would be limited electronically to around 186 miles per hour. The agreement was not publicized, but it was adopted across the board. After that point, speedometers changed. Later, Hayabusas and competing machines came fitted with gauges that stopped well short of the 220 miles per hour mark. Some were limited to 185, others to 190, but none showed the same full arc. The early GSX 1300R stood alone, not just as a record setter, but as the final expression of an unrestrained design era. Today, collectors often look for that original speedometer as a sign of authenticity. The long needle, the full sweep, and the final number at the edge of the dial are not cosmetic differences. They are evidence of a brief moment in motorcycle history when top speed was still being chased openly. Number 5. Delicate aluminum rear subframe that was later swapped. Sometimes it is not the engine, the brakes, or the suspension that reveals the most about a motorcycle's development. Sometimes it is the part that breaks. In the case of the 1999 Hayabusa, that part was tucked quietly behind the seat. It did not contribute to speed, power, or handling, but it became one of the few weak links in an otherwise overbuilt machine. That part was the aluminum rear subframe, and while it helped keep weight down and lines clean, it did not stay on the bike for long. The rear subframe on the early GSX 1300R was constructed from lightweight aluminum tubing. It was welded in a minimalistic, triangulated shape that supported the rider seat, passenger seat, and rear bodywork. For most solo riders, it performed its job without issue. It was light, rigid, and resistant to corrosion. But it came with limits, and Suzuki found those limits the moment owners started modifying their bikes. As aftermarket exhaust systems became popular and passenger accommodations were more frequently used, the rear subframe began to show signs of strain. Cracks formed near the upper welds. Cross members started to distort, and in some cases, the entire structure bent under load. The subframe was never designed to carry excessive weight, nor to resist the torsional stress introduced by heavy accessories or top-mounted luggage racks. What was ideal for performance became a liability under real-world conditions. The problem became more pronounced when riders began adding hard cases, reinforced tail sections, or riding with heavier passengers. With the added mass sitting above and behind the axle, the forces acting on the subframe increased exponentially over bumps or under throttle. The result was premature fatigue. In the worst cases, the subframe collapsed entirely, taking the tail fairing and electrical harness with it. Suzuki responded quickly. In the following production run, starting with the year 2000 model, the company replaced the aluminum subframe with a heavier, more durable steel version. The design remained visually similar, but the material change provided a significant increase in strength and load capacity. The new subframe could tolerate higher static and dynamic loads without deformation. For most riders, the change went unnoticed, but for those pushing the limits of the original design, it made a real difference. There was no official recall, and Suzuki did not issue a press statement. The update was made quietly, as a rolling correction to an issue that had not yet reached critical volume. Dealers began retrofitting the steel subframes when warranty claims were filed, and by the middle of the year 2000, nearly all new Hayabusas were shipping with the upgraded component. The original aluminum version faded into history, remembered mostly by owners who had to replace it themselves. What makes this detail surprising is how rare it is to see a structural downgrade in material reversed so quickly. Manufacturers often chase weight savings aggressively, and aluminum is nearly always favored for non-load-bearing parts. But in this case, Suzuki chose long-term strength over minimal weight, and that choice made the bike better. The aluminum subframe was a clever idea in theory, but it could not survive in the real world of passengers, modifications, and hard miles. And while it may have saved a few pounds, it also taught a quiet lesson. Even the most capable machines can fail if one piece is too light for the load it must carry. Number 4. Hard to spot early ECU with no speed limiter. There's no badge on the tail section, no difference in the wiring, and no visible sign from the rider's seat. But on a select group of early GSX 1300R models, built during the first production run in 1999, there's a small, easily overlooked component that quietly separates them from everything that came after. It is not a mechanical upgrade or a cosmetic variation. It is an internal difference, hidden inside the engine control unit. And for those who understand what it means, it marks the end of one era and the quiet beginning of another. The ECU, or engine control unit, is a sealed electronic module responsible for managing fuel delivery, ignition timing, throttle response, and various engine safety parameters. On the Hayabusa, it operated in real time using sensor data to balance performance and efficiency across the rev range. But on those earliest bikes, the ECU lacked one now standard function. It contained no limiter. There was no electronic sealing, no programmed intervention at top speed, and no software restriction designed to cap the bike's maximum velocity. The early mapping allowed the engine to continue building speed well beyond what later models would permit, and it did so without warning, hesitation, or artificial cutoff. The timing of this omission is what makes it significant. In the months following the Hayabusa's release, concerns began to emerge from European safety groups and transportation regulators regarding the rapid increase in motorcycle top speeds. Rather than face mandatory legislation, the major manufacturers entered into an informal agreement known today as the Gentleman's Agreement. Beginning with the 2000 model year, all new high-performance motorcycles would be electronically limited to a top speed of approximately 100 kilometers per hour, 186 miles per hour, regardless of their actual mechanical potential. This agreement changed the way future sport bikes were designed, and it placed an invisible barrier where none had previously existed. Suzuki implemented the change by revising the ECU. Later units were programmed with a speed-limiting algorithm that softened acceleration near the cap, gradually tapering engine output to ensure that riders could not exceed the new maximum even under ideal conditions. The limiter was not abrupt, and it did not trigger a warning light. It was subtle by design, written to feel natural and non-intrusive, but it fundamentally altered how the machine behaved at the edge of its performance envelope. What makes the early ECUs so unusual is how quietly they disappeared. There was no recall, no formal announcement, and no external indicator. The only way to confirm whether a bike carried the unrestricted version was by checking the part code, cross-referencing production dates, or verifying the software against known baseline maps. Owners who discovered the difference often swapped units or preserved them for future tuning. And over time, these early ECUs became one of the few ways to experience the Hayabusa exactly as it was originally intended. For most riders, the difference may never be noticed. The engine still pulls hard, the acceleration remains fierce, and the speed feels limitless. But for the ones who know what is inside, that early ECU represents something more than performance. Number 3, early clutch spring mod fixes a harsh engage behavior. Not every change on a motorcycle is driven by performance or regulation. Some are the result of rider feedback, small patterns noticed over time, and quiet corrections made without fanfare. On the 1999 GSX 1300R, one such correction involved a component few riders ever thought twice about: the clutch springs. The original clutch assembly was strong, precise, and fully capable of handling the torque produced by the engine. But in the early months of release, a pattern began to emerge. Riders were reporting the same issue across different conditions and setups: an abrupt, sometimes jarring clutch engagement that made smooth takeoffs difficult, especially in low-speed or stop-and-go situations. The Hayabusa was not suffering from a mechanical failure. Nothing was broken. The plates, basket, and actuating components were all well within expected tolerances, but the clutch behavior at low revs felt unrefined. Some described it as grabby, others as unpredictable, with the friction zone coming on too suddenly for a bike that otherwise felt composed and deliberate. The issue was especially noticeable during urban riding, parking maneuvers, or slow turns where throttle control and balance were critical. For a machine built with high-speed precision in mind, the lack of finesse at low speed stood out. The problem was traced to the factory clutch springs. Suzuki had selected a relatively stiff spring rate to ensure slip resistance under full throttle loads, particularly in top gears. In that regard, the setup performed exactly as intended. The clutch held firm at speed, resisted fade under heat, and transferred power without hesitation. But at the lower end of the rev range, the stiffer springs created a sharper engagement profile that gave the lever a narrower friction zone. The result was a clutch that felt more like a switch than a sliding surface. Rather than issuing a recall or a bulletin, Suzuki addressed the issue quietly. By the time the year 2000 models entered production, a revised clutch spring setup was already in place. The updated springs featured a slightly lower rate, offering more progressive engagement without compromising load-holding capacity at higher speeds. Internally, the part numbers were updated, and dealers began receiving the new springs in standard service kits. Many owners who brought their bikes in for unrelated maintenance during that window had the new springs installed without even realizing a change had been made. The new springs improved low-speed control noticeably. Lever effort remained firm, but became easier to modulate. The transition from static to moving was smoother, especially when riding with a passenger or during frequent starts and stops. More importantly, the change restored consistency across the rev range. The clutch no longer felt like a performance compromise, but returned to its intended role: predictable, strong, and transparent in function. Today, finding a first-year Hayabusa still running the original clutch springs is uncommon. Most have been updated, either during service or by owners seeking better control. For those who remember how the early clutch felt, the change was welcome, even if it went undocumented. Number 2, leak-prone chain tensioner recall on first few hundred bikes. Not every issue leaves a visible mark. Some remain tucked beneath covers, detected only by sound, feel, or a careful technician. In the earliest batch of GSX 1300R models, built in 1999, one such issue emerged quietly, traced back to a single component deep inside the engine case, the cam chain tensioner. It was not a catastrophic failure, it was not dramatic, but it was serious enough for Suzuki to step in quickly and quietly. The cam chain tensioner is a small hydraulic device responsible for keeping the engine's timing chain under constant pressure. In most cases, the part operates without attention for tens of thousands of miles. But in the first few hundred Hayabusas that left the factory, the original tensioner began to show signs of premature wear. Under certain conditions, it failed to maintain proper pressure on the chain, especially during cold starts or after prolonged idling. The result was not always immediate failure, but it created conditions where timing could drift, mechanical noise could increase, and oil could begin seeping from the mounting area. Reports reached Suzuki within months of the model's release. The issue was not widespread, but it was consistent enough to raise concern. Rather than wait for larger-scale problems, Suzuki issued a targeted recall for affected units. The revised tensioner featured an upgraded internal mechanism with more consistent oil retention and improved spring reliability. Unlike the original, which could allow momentary slack in the timing chain, the new unit held pressure more reliably across all conditions. The installation was simple and often performed during routine servicing. Most dealerships received the part as a warranty item, and many owners never experienced symptoms before the update was installed. For those who did, the warning signs were subtle: a brief rattle at startup, a faint ticking noise near the top end, or a light mist of oil near the rear of the cylinder block. These signs disappeared once the new tensioner was in place. The change did not alter performance. Horsepower remained the same. Acceleration was unaffected, but what it restored was mechanical consistency. The engine returned to running with the composure expected of a machine built for extreme loads and sustained high-speed use. Few motorcycles launch with perfect components across the board. What matters is how a manufacturer responds when something slips past the line. Suzuki's fix came early, without hesitation, and without the need for a public campaign. Number 1, shocking speed record that forced a speed cap agreement. In 1999, Suzuki did not aim to match the competition. It aimed to pass it in one clear metric: top speed. The GSX 1300R became the first production motorcycle to exceed 190 miles per hour, with verified testing showing speeds as high as 194 miles per hour. That figure did not just set a record, it created a problem. Before the Hayabusa, the top spot belonged to the Honda CBR 1120, which reached 178 miles per hour. That number had held for several years. Suzuki's goal was not to beat it by a small margin. The company designed the Hayabusa to surpass it by a measurable gap and hold the title without debate. The result was not a speculative figure. Independent testing confirmed the Hayabusa's top speed, and there were no factory limitations in place. It ran to its mechanical limit, without electronic intervention. The response to that number came quickly. Within months of its release, regulators in Europe raised concerns about motorcycle speeds entering territory, typically reserved for dedicated racing machines. Manufacturers recognized the risk. There was concern that continued escalation could trigger formal restrictions, safety legislation, or import limitations. Rather than face government regulation, the major motorcycle brands reached a private consensus. By the year 2000, a voluntary agreement was in place. All new high-performance motorcycles would be electronically limited to a top speed of approximately 186 miles per hour. The agreement was not announced publicly, but its effects were immediate. Later Hayabusa models, along with offerings from other manufacturers, arrived with ECU programming designed to taper engine output near the agreed limit. The restriction was gradual, and the rider would not encounter a sudden cutoff. But the outcome was clear. The earlier unrestricted speeds would not be repeated under factory settings. This placed the original 1999 Hayabusa in a category of its own. It was not only the fastest production motorcycle at the time of release, but also the last one built before the introduction of electronic speed limitations. That distinction is not visible on the frame or the fairing. It is only confirmed by production date and engine control programming. Bikes produced after the agreement took effect were subject to the limit, regardless of market. The Hayabusa's performance record was not based on claims or projections. It was achieved, measured, and responded to. The figure of 194 miles per hour became the trigger for an industry-wide cap. And for one model year, the GSX 1300R remained ungoverned by software or restriction, marking a clear end to open top-speed development in production motorcycles. The 1999 Hayabusa was not just a fast motorcycle. It was the one that changed what fast meant. Behind its reputation are decisions, risks, and corrections that defined an entire category. Have something to add to the record? Leave a comment, hit like if you respect the engineering, and subscribe for more.